The last thing that we'll talk about in this section is differential equations. And differential equations are equations involving an unknown function and its derivatives. So for example, we might have something that looks like xy prime plus y double prime is equal to 2xy, where y is a function of x, and we're looking for a function of x. This would be the derivative of that function. This would be the second derivative of that function. And we would be looking for a function of x that we can plug in for y, and that makes this equation true. It turns out that that's a pretty difficult task. So differential equations actually ends up being a really deep topic. You can take whole classes on differential equations. Moraine Valley actually offers a differential equations class. So there's a lot to this topic. We are going to look at just a couple of fairly simple examples. Here in these two examples, we just want to solve the initial value problem. So here I'm given f prime of x, so I'm given the derivative. F prime of x is equal to x squared minus 2x. And then this time I'm also given another piece of information. It says that f of 1 is equal to 1/3. And what this is actually giving me, this is giving me a point that's on the graph of f of x. So this means if I were to graph this function, it's going to pass through 1, 1/3. And I don't really know what the rest of my function looks like, but it's going to go through this point right here. And it turns out that as soon as we have one single point on our graph, that's going to determine what antiderivative I'm talking about. I should say which specific antiderivative that we're talking about. And actually, I'm going to scroll back to one of the very first pictures we looked at here. Remember we said, okay, here's all of these different antiderivatives, and we might be talking about, let me just highlight it. We might be talking about, say, this particular antiderivative, the purple one that I'm highlighting here, but I don't know how to get that across. But if you tell me that my function passes through, let's see, 1 comma, this looks like 1 comma 8 right here, 1 comma 8, then I know immediately that I'm talking about this purple function that I'm tracing right now. So that actually tells me which specific antiderivative it is, and then that tells me, it gives me a way to solve for c, and I can figure out, oh, well, c is equal to 7 in this case. So as soon as I have one single point on my graph, I can actually find the specific antiderivative rather than the general family of antiderivatives or the indefinite integral that we've been talking about so far. So I'm starting with the derivative. I want to work my way back to the original function because at the end of this, I'd like to be able to say f of x is equal to blank and then give the actual function. So I'm going to integrate my derivative. So I'm going to integrate x squared minus 2x dx. So this is not too bad. It's just a polynomial, so I need to use my power rule. So I will add 1 to my power, x to the third, divide by my new power of 3, minus over here, add 1 to my power, 2x squared, divide by my new power of 2, and then, of course, plus my constant of integration c. So maybe we'll clean this up. We'll say, okay, this term is just x squared, and right now, this is my f of x. But this isn't really a great answer because I would really like to know, well, what is my constant of integration? Which specific antiderivative are we talking about? So that's where this point is going to come into play. This f of 1 is equal to 1/3. What that's really telling me is that when x is equal to 1, my function takes on a value of 1/3. So if I was to look at f of 1, this is 1 to the third over 3 minus 1 squared plus c. This is equal to 1. And this actually gives me an equation that I can solve for c. And actually, let me rewrite this over here because I just don't think I'm going to have enough room. That we said f of 1, that's equal to 1 to the third over 3 minus 1 squared plus c is equal to 1/3. So I'm just going to essentially look at this part. I'm going to look at that equation and solve for c. So I should have 1/3 minus 1 plus c is equal to 1/3. 1/3 minus 1, let's see, that would be negative 2/3 plus c is equal to 1/3. So if I add 2/3, c is equal to 1. But this is not my final answer, because what I need to do then is take this c equals 1 and plug it into my function. That function is my answer. That's what I want to give. So my differential equation, that is the solution to this initial value problem, is f of x equals, we'll write it down here, f of x equals x to the third over 3 minus x squared plus c, but we just said, hey, c is 1, so plus 1. This is the solution that we're looking for. So these are kind of the exception to the rule where we're not going to have that plus c. Well, we won't end with a plus c. We actually do still have our constant of integration c. We just have this extra added step now, just this little bit of algebra where we want to go and solve for c. Next, I have g prime of t is equal to 1 plus 6 sine of t, where I'm told g of pi over 3, that is equal to negative 3. So again, I'm starting with the derivative. I want to end up with g of t, the original function, is equal to blah. So I want the antiderivative. I want to integrate this function. And I think, I've got a lot of room here. So I want to integrate 1 plus 6 sine t dt. So I'm going to integrate this function. So if we haven't noticed the pattern by now, when we integrate a constant like 1 here, I've been saying, oh, well, that's really 1t to the 0. What ends up happening when you integrate a constant is you're just going to pick up a factor of whatever that variable you're integrating with respect to is. So here we're integrating with respect to t. So I really have just 1t, but we would probably just write that as t. So t plus, here we need to be a little bit careful. We've got a trig antiderivative that we need to find. So let's see, that's 6. No, that's a constant multiple. That's just going to come down. And let's see, antiderivative of sine of t. Maybe I think, okay, that's cosine of t plus c. But remember that we can always double check our work. If I take the derivative of 6 cosine of t, if I were to take the derivative of that, that would give me negative 6 sine of t. So I know that I'm off by a negative sign. I shouldn't have 6 times cosine of t. I should have 6 times negative cosine of t. Or perhaps t minus 6 cosine of t plus c. So here is my current g of x, or g of t, I guess in this case, excuse me, g of t. And I would like to now use this initial condition. I have g of pi over 3 is equal to negative 3. I'm going to use that initial condition to solve for c. So let's do that in a different color here. So g of pi over 3 is equal to t. Well, I just have to plug pi over 3 into that. Minus 6 times cosine of pi over 3 plus c. And what is this equal to? This is equal to negative 3. So I have this equation where I can solve for c. Let's see, pi over 3, that's not really going to simplify. So let's just leave that as pi over 3 for right now. Minus 6, here I need to look at cosine of pi over 3. Pi over 3, let me think for a moment. That's in the first quadrant. That is the same as 60 degrees, the x-coordinate there. That should be 1/2 plus c is equal to negative 3. So, okay, I have this function. Let's see if we can solve for c now. So let's see, pi over 3 minus this is 3 plus c is equal to negative 3. If I add 3 to both sides, I have the really nice case where, okay, these two cancel, and then subtract pi over 3 minus pi over 3, I end up with c is equal to negative pi over 3. But remember, that's not how I want to write my answer. I still need to take this and plug it back into the function that we found earlier. So my answer here, the solution to this problem, would look like g of t is equal to t minus 6 cosine of t. But rather than have this plus c, we said, hey, that's c. That's equal to negative pi over 3. So plus negative pi over 3. Or, of course, you could write minus pi over 3. And this is what we are looking for. So in these types of problems, these differential equations problems, we are looking actually for an equation. It's actually an equation or a function that is going to be our solution to the problem. And differential equations are cool because we can actually use them to help us solve some of those motion problems that we actually talked about way back in, I believe it was 3.6 that we talked about. Now we can kind of go backwards from those and say, okay, if we start with acceleration, can we work our way backwards to velocity and then work our way backwards to position? So we'll actually look at that in the next video.